it does to 6 people. Now there's like 4 Catan boards between all of us, so we can fit like 20 people. And I've bought like $100 worth of board games since then. So we can kind of expand if you guys are here on campus, want to play games with us Tuesday night. The other thing I want to say, I forgot to bring it up on the screen. There's a slight change. There's two changes that are going to be made on the homework that are general. The one is specific to homework 3. I'm not changing the homework grid. I got to. All right, fine. I guess it's my 30 days today. And of course, it's not popping up on my phone. What's it called? There we go. I had to. This class got selected for official assessment by the department, by the school, even by the provost office. So I have to do an assessment on one homework set on one homework. So homework 3 is being assessed externally. I assess them, and it's just an evaluation I do. The only thing that changes is that you have to now submit your problem set in the external website. So you just click that. There's a tutorial at the top on how to do it. Nothing's different. All right, so just submit your PDF through that external website. I'll grade them like normal, send you feedback through Canvas. Everything is the same. This does not make any difference to you. It's only for me and for internal purposes. There's something I'm required to do. So those are the only 2 announcements I have. One more. It's going to change for homework 4. I had some comments, some suggestions from students. I'm going to shift the due date schedule on the homework a bit. So right now it's due on Fridays, and then the submission window open until Tuesday. What I'm starting to realize is that typically I post homework on that Monday in between. That people going into Tuesday, that first Tuesday section tends to be kind of not synchronized. People on the old homework, procrastinators on the old homework. Some people are way ahead on the new homework. They've already started it. Some people are just starting it. It's kind of a pain in the butt that first week. So what I'm going to do starting homework 4 is I'm just going to make everything due on Tuesday now in the evening. It'll be Tuesday, 11:55. And that's going to be a hard cutoff. So I'll still give you like 2.5 weeks. It's still the same extension. All right. But instead of it being open on Friday, it's going to be open on Tuesday or closed on Tuesday, hard. And then I will post the next homework that night after the session, so Tuesday evening. It doesn't change any of the requirements. It just makes sure everyone is now synchronized on their homeworks for the LA session. So that'll be the only change. So if you're the kind of person who gets it done really quickly, the only thing that's happening is instead of me posting it on Sunday or Monday, I'm going to post it on Tuesday night. But then it'll be you'll have an extra weekend to do it. All right, any questions about that? Okay. All right, I want to have a quick aside today to kind of close out the week. We're about halfway through the class as of today. I want to make sure we're all on the same page about a somewhat important but somewhat boring topic. And then we'll go back to vibrations. But I think it's good to talk about this, and it's not a conversation we've had yet. Is units of energy. All right. One of the things that we're going to see in this class, and you might have already started to see if you started in these homework, there are a lot of different units we use. There's a lot of different conventions. And I want to talk specifically about the energy conventions for energy units. Because what we're going to be doing is we're going to be looking at energies from the point of view of a spectroscopist, which is really what we mean when we talk about energy levels and stuff, right? We're going to do spectroscopy. That's how we interrogate these things. And we use different units for energy depending on what type of spectroscopy we use. Okay, and I'm somewhat sloppy in the sense that I tend to jump around just out of convention. And I want to make sure we're all on the same page. Okay, so some of this might be review for you. Some of this might be really boring. Some of these units you've maybe never even heard of or even thought about. But I want to talk about the different types of units we use for energy in chemistry, and then do some conversions. Okay, so we all have the same page and we can move around between units freely. All right, the big kind of organizing principle of our energy units in quantum mechanics is just one equation. Which is just E equals h nu, Planck's law. Right? And Planck's law allows us to really interconvert between just about everything. Right? Already it gives us a really nice conversion, right? We always start with our baseline energy unit, which are joules. Right? That's the one we used all last semester. But Planck's constant gives us a conversion into frequency, right? E equals h times the frequency of the light corresponding to that energy. Right? So from Planck's law, we get the frequency unit of energy, right? Which is going to be the energy divided by h, which is a frequency, and it's in inverse seconds or hertz. Okay, and I just want to be very clear that when I mean hertz, this is the amount of time it takes to cycle 2 pi radians. So this is the time it takes to travel 2 pi radians of a period or a whole period per second. All right, so that's a little different than the other type of frequency that we sometimes talk about, which would be E over h bar, which is omega. We often write that as omega, which is radians per second. Right? I don't even need to write anything, right? So the conversion, of course, between these is that V or nu is 2 pi omega. Okay. So the idea here is just very obvious, right? If we have some sort of oscillating object, whether it be a light particle, photon, or an electron oscillating at some frequency, it has equivalent energy h nu. So this allows us to convert between light energy, photonic waves, wave properties of light, wave properties, particles to mechanical energy, joules. Okay. Again, we use this kind of conversion in thermodynamics. We use the gas constant, right? The gas constant takes us from temperature, which is a measure of average thermal energy, into something that is joules, Kelvin joules. So H works the same way. H takes a frequency of a wave and converts it to energy. It's the energy equivalent of the frequency of light. Okay, so when do we use frequencies? Well, frequencies are really useful when we're talking about, again, mechanical oscillations of the system. Like vibrations or some sort of wave oscillating. There are very natural ways to use it. It is used in spectroscopy, though. Typically, let me give you some examples. So some examples of the uses of frequency. One is an NMR. In NMR, we often talk about either the size of the magnet, but the magnetic strength of an NMR is often converted to a frequency. Tells you how much energy the two spin states of a proton are split by. So NMR tends to be, the units of energy for an NMR experiment tend to be on the order of 40 times 10 to the 6 hertz to 10 to the 9 hertz. And this is the same, of course, as 40 megahertz, and 10 to the 9 is 1 gigahertz. All right, so NMRs, we say in some sense the oscillations, the resonant oscillations of spin, and an NMR experiment of a proton, a hydrogen atom, whatever you want to think about, those tend to, they're instrument dependent, but they tend to be somewhere between 40 megahertz and 1 gigahertz. Okay, so upstairs in Buckman, our little solid state NMR that runs at 43 megahertz. Okay, so the light that's being broadcasted and emitted in that system is at that frequency. And so we could easily convert that into joules, right? But you can see why that's a really annoying thing to do. Right? This is a really nice number to write, right? 40 megahertz is really nice, but what's the joule equivalent of that? Well, the energy equivalent of that would be 40 times 10 to the 6 times 6 times 10 to the minus 34. Okay, so the amount of joules contained in 40 megahertz is around 10 to the minus 27, 10 to the minus 28 joules. It's a really, really small number. All right, so when we're working in low frequency or long wavelengths, we'll get back to wavelength in a second. We just ignore joules altogether. We just throw away joules. They're completely worthless. They're not helpful numbers. We use the frequencies instead. Or we haven't introduced this yet, but when we get back, we will. And this is my field of expertise, rotational spectroscopy. So the rotations of molecules. These tend to be between, let's say, 2 gigahertz and 300 gigahertz. Right, at this point, right, 300 gigahertz, we're starting to get to kind of what I would call big numbers. You know, what you'll find as we go through this class is that as we start to learn about new physics or new types of motion in molecules, electronic or vibrational, we tend to pick a unit of energy that's typically represented with a small number at that scale. Right, so that's why we use it. That's why we use megahertz for NMR, because the energies in NMR are kind of on the order of megahertz, maybe 100 megahertz. Rotational spectroscopy is on the order of 1 to 10 or 100 gigahertz. It's a very logical number to use, right? Just it's very convenient for us, right? The last thing we want to do is when we're talking to each other to communicate information to each other, where we got to add exponents, right? 10 to the minus 28, 10 to the 5, 10 to the 7, things like that. Those are places where, as you guys may know from your homework, it's easy to screw up, right? And communication-wise, it's very difficult to communicate very small numbers or very large numbers precisely. So that's why we tend to use frequency as a convenient unit. All right, we can convert between joules and frequency. We can see how many units of frequency is 1 joule. Let's just do that really quickly. So a quick calculation at the bottom. So 1 joule is equal to h bar omega. Right, so omega for 1 joule is 1 over h, which is a huge number. It's 1 over 6.02, 2 times 10 to the 23rd. Oh, sorry, it's did I get that wrong? Yeah, 1 joule over h. Sorry, I put Avogadro's number in my math. Sorry. 6.0, what is it again? 6.636, sorry. So this is 1 joule. This is a 1 divided by 6.636 times 10 to the minus 34 joule seconds. And you can already see you're going to get a frequency here. You're going to get inverse seconds, and it's a big number, right? 1 divided by 6.636 e minus 34 is 1.5 times 10 to the 33 hertz. Right, that's a big number. Okay, let me just put it this way. This is more energy than a typical collision in the Large Hadron Collider and switcher. Right, so those two, the Large Hadron Collider is a proton-proton collider. It collides them together, 2 protons together, and the average collision energy in the LHC is about half a joule. All right, so this is in some sense bigger than any energy that you can get in the world by about a factor of 2 or a factor of 5. right? So 1 joule is in terms of a quantum mechanical number, 1 joule is a huge number. It's a huge amount of energy. Right? We're more comfortable with the idea of joules per mole. Right? 1 joule per mole is a very little amount of energy, very small amount of energy chemically, but we're also counting it over 10 to the 23 molecules. A joule is just the energy contained in one particle. Right, so to have a joule in of energy contained in, say, a single proton, that's a lot of energy. Right. You can kind of calculate that roughly that the macroscopic energy of collision of 2 protons in the LHC, which is about half a joule, is about the equivalent of getting someone pitching a fastball to your head. Right, so that's kind of what you're looking at. It's a lot of energy for a microscopic particle. Here's a popular pitcher right now. The only one I can think of is Aroldis Chapman. He throws at 105 miles an hour. That means his baseballs have about 1.5 joules of energy. I don't even know if Aroldis Chapman pitches anymore. Okay, so that's frequency, and very convenient. We can always interconvert between frequencies and wavelengths. So wavelengths are also a very useful unit of inverse energy. Right, wavelength. Right, we can always convert wavelength and frequency by dividing using the speed of light. C over lambda. Right, so this means that we can always interconvert between energy and wavelength. This is a tricky unit to use for energy. And the reason why is because differences in energies are differences in the inverse wavelength. All right, so the math doesn't always work quite as simply as you would like for energies. You'd like to subtract 2 energies and get a new energy out. And so you'd like to say, okay, well, let me just subtract 2 wavelengths and get a wavelength out. That's not how it works. Because what delta E is here between, say, 1 and 2 is HC divided by 1 over lambda 2 minus 1 over lambda 1. All right, so the math is inverted for inverse energies, right? So sometimes using wavelength as a analog for frequency or energy can get you kind of in trouble, as the scale is inverse, not linear. But it's still a useful number, right? And we can just think again very simply about what's the energy content of a photon at some wavelength. So let's just think of something. So like a green photon, so a green laser is at lambda equals 532 nanometers. Right, so how would we calculate the energy of that? Well, it's 6.636 times 10 to the minus 34 joule seconds divided by the speed of light, which is 299,792,458 meters per second, defined exactly, divided by 532. We got to put it in meters, of course. It's 10 to the minus 9 nanometers. So it's 532 times 10 to the minus 9. And so the energy of a 532 photon in joules is this number. Let me go ahead and just quickly calculate it for you. It's 3.73. Well, it says 3.74 times 10 to the minus 19 joules. Again, that seems like a small number, but let's multiply it by Avogadro's number. 6.022 times 10 to the 23rd per mole. Right, and you can see we're already kind of on the order of 10 to the 5 joules per mole here. This is, yeah, it's 225, 193 joules per mole. Is that right? Yeah, that's right. Which is 225 kilojoules per mole. Okay, that's a lot of energy, right? You can see that, there's quite a bit of energy in an optical photon. We're already getting to the point of carbon hydrogen bond, for instance, is about 400 kilojoules, right? So you're already getting to about a factor with visible photons. You're already getting to within about a factor of 2 of bond strength. If you absorb that energy, it might blow a bond apart. And that's in fact exactly the case. If you go to say 210 nanometers, about half this wavelength, right now you're at about 500 kilojoules per mole. And organic molecules left and right absorb like crazy at around 200 nanometers. Methanol absorbs, acetonitrile absorbs, iodine is disassociated at that point. Right, you're getting to the point now at at optical photons, you're starting to get to the point of chemical amounts of energy. So this is actually, again, this should give you a nice hint. This is a really good way to supply energy to a molecule to drive a reaction, is to blow it apart with a laser. Right? We should probably, maybe a nice calculation to do is to think, well, if we had a furnace and we wanted to blow our molecule apart with heat, and it would need this much energy, what would the energy, what would the heat, what would the temperature of the furnace have to be to achieve 225? Right, so let's just think about that. Right, compared to (225 kilojoules per mole) is equal to R times some temperature. Right, this is the idea. You have a kiln or some sort of forge that runs at some temperature. You want to supply an average amount of energy of about 250 to it. What do we get? Well, T is going to be 225 kilojoules per mole. And the gas constant in these units is 0.0083145 kilojoules per mole. That's a big number, as you can see. Go ahead and calculate it for you. Right, this is 27,000 Kelvin. Right, there is no furnace outside of the sun like it's that hot. All right, so this is why thermal degradation of molecules tends to be kind of a really bad way to do chemistry. There are exceptions, of course, but in general, thermal energy is a really poor way to get energy into a molecule, because in order to get chemical amounts of energy into a molecule, have chemical amounts of energy available to you, you got to heat it to, to solar levels of intensity. At 27,000 Kelvin, actually, at that point, you're actually hot enough that the hydrogens lose their electrons. Right, you're ionizing the atoms. Right, which is what happens in the sun. Most of the hydrogens get ionized with H+. There is no hydrogen, neutral hydrogen on the sun, only in the exterior. And so at this point, you're breaking apart atoms. And so this is why lasers end up being a very, very powerful way to do chemistry, to induce chemistry, because a single photon gives you 225 kilojoules per mole equivalent. Right? You need a mole of photons and you get that energy. That's a lot of energy really quickly. And a normal laser pointer almost has a mole of photons per second. So it's a lot of energy. The reason why your 532 nanometer green laser pointer, like one ion, doesn't immediately nuke your skin, it's because everything, organic material is transparent at this region. It doesn't absorb it. So it's not really a big deal. And also the intensity, how many photons are, another important part of lasers is how focused the beam is, how many photons per square centimeter of interaction point, the surface area of the interaction. Laser pointers aren't that intense. But a high quality commercial class 4 laser really will burn your skin very effectively. In fact, we used to troll each other in lab because the 532 nanometer laser actually is a comes from a 1064 nanometer laser. You double the wavelength. And 1064 is invisible to the eyes, but there's a lot of power in there. My grad student colleague, while he would tune his 1064 laser, I'd be working in a corner on an instrument or something like that, and he'd turned the mirror towards me, and then pop my skin on my arm with it or something, and you hear a little pop. And the 1064 like oxidizes the skin. It's kind of a fun thing to do with your friends. Don't tell your boss that. That's really breaking a lot of laws. But it's fun. Infrared lasers will do that too as well. Okay, so that puts us in the wavelengths. So again, the problem with wavelengths though is that if you want to calculate energy differences, it's a real pain in the butt. Everything's inverse. So what that means is that the difference between 1 nanometer and energy at 600 nanometers is different than it is at 300 nanometers because the fractions are 1/301 minus 1/300 is different than 1/601 minus 1/600. They're inverse scales; they don't scale linearly. So wavelength can be kind of annoying, but people are clever and have decided to, well, instead of worrying about wavelength, what if we think of inverse wavelength instead? So that's what's called a wave number. Right, and typically wave numbers are notated either with a little squiggly, sometimes with a V or a V like this. Usually the tilde, the little squiggly, means wave numbers. All right, and a wave number is just 1 over the wavelength. All right, so this has units of inverse length. That's a really convenient unit, right? Because now what we have, is that the energy in joules is hc times the wave number, right? So now the energy scale is linear again, because now you can compare wave numbers to inverse wavelengths. And those are linear; they're just normal numbers. So anytime you see a wave number, something inverse length, think energy, right? It's energy times hc. Right? We often use, so the most common unit, as anyone's done infrared here knows what it is 1 over wave CM minus 1, right? And this is what we call wave numbers typically. So it's very rare that we represent wave numbers in anything other than inverse centimeters. And the reason why it's inverse centimeters is 100% due to like historical reasons. All right, the reason why, we can just do a quick calculation. All right, so CM minus 1 is convenient for infrared. Red spectroscopy. Right, because one wave number, so if omega is one wave number, that means that the wavelength is 1 centimeter. All right, so it's a very nice unit, and the frequency, the equivalent frequency of this, it's exactly 29.979 gigahertz. All right, so wave number, so CM minus 1 in some sense is a really natural extension of gigahertz. Right, so we look at NMR in the radio, then we have microwave for rotational spectroscopy in the microwave, that's gigahertz. And then we start to get into things that have wavelengths of 1 centimeter or smaller, and those start at 30 gigahertz. Right, so if you think about a typical IR experiment, right, typical IR experiment, is that, like, let's say 2000 wave numbers, right? So that means that the wavelength is 1 over 2000 centimeters minus 1, right? And I'll just, because I'm lazy, I'm not going to do that math in my head. So that's 5 times 10 to the minus 4 centimeters, which is 5 times 10 to the minus 6 meters, which is 5 microns. All right, so when you're in the micrometer range of wavelengths, that means you're kind of in the tens to thousands of wave numbers, right? And that's what we typically do in infrared spectroscopy. Okay, that's just so it's just a very nice number that gives us kind of unit length with useful wavelengths in the region, and keeps our numbers small. Right, keeps it below. There's no exponents. The biggest wave number that you're going to measure in infrared typically is on the order of maybe 5,000 or 6,000 wave numbers. Right, so it's a really nice convenient. All right, let's just do a couple conversions. I think they're really useful to convert. Wave numbers in particular are so useful because they're used in spectroscopy all the time. They're used not only to represent the wavelength, the absorptions or the emissions of a molecule, but spectroscopists and physical chemists will use wave numbers as a substitute for joules per mole and kilojoules or kcals, and they use it for thermodynamic units as well, because it allows you to compare and contrast different values, right? We just like to have one unit. It's kind of annoying to have some things in wave numbers and some things in joules. So wave numbers turn out to be a really useful number for just about everything in the chemical range. They're never too big, they're never too small. And so some conversions we can do. One wave number again is 29.979 gigahertz. And let me get the rest of them for you. I have a big, I always forget all of them off the top of my head, but I have a little conversion chart right here. So this is equal to 11.96 joules per mole, or 1.44 Kelvin. Are there any other useful units? And of course, this is a 1 centimeter wavelength as well. Right. So this is why I really like wave numbers, why wave numbers are really useful. Right, they're on the order of a joule per mole. They're on the order of a Kelvin. If you're thinking about thermal units, think about temperature. Right, so it's a very convenient unit to use. Everything is kind of close together. It's kind of like a nice Goldilocks unit for chemistry. Okay, it just kind of sits in the middle of the scale. Right, it's kind of smaller than a lot of things, but it's not too small. It's bigger than some things, but not too big. All right, so we use wave numbers a lot. It's a very common unit. The final unit I want to introduce, and this is about the only other unit that spectroscopists use. Yeah, the only other unit. And this is typically used at much higher energy than what we've talked to, kind of in the X-ray and in the ultraviolet. So this is the high energy unit. Which is an electron volt. Right, so we typically write electron volts as EV with the lowercase e. Right, and of course you might wonder what the hell is an electron volt. All right, so 1 EV defined exactly in some sense, or what that kind of conceptual definition of it is, the kinetic energy required to accelerate, or sorry, the kinetic energy gained by an electron. Yeah, let me erase this. Let me get my words perfectly right. When accelerated through a 1 + 1 volt potential difference in the vacuum. Right. So if we have, say, like 2 plates in the vacuum, we have one that's negatively charged and one's positively charged. Yeah, and then we have 1 + 1 volt going into here. Right, the electrons move across this potential. 1 volt. And the energy of them, the energy of these electrons is 1 electron volt. Okay, so 1 EV by definition is 1.602 177 times 10 to the minus 19 joules. And that just comes from the charge of the electron, which is a fixed value. And let me get some other units for you really quickly. Yeah, so this is about 8,065 wave numbers. Or this is the one I always remember. It's about 96.48 kilojoules per mole. And it's about 11,600 Kelvin. Yes, ma'am. Oh, sorry. Yes, 8,065. I'm sorry. I get a frowning face for my sixes. 8,065 wave numbers. All right, so we can quickly calculate what the wavelength of a 1 EV signal is, right? Because we have the inverse wavelength. So just a quick comment here. The wavelength would be 1/865 centimeters. Which is 1 point. Oh, I'm sorry, I just lost my calculator. I apologize. Computer's got a mind of its own today. 1.24 times 10 to the minus 4 centimeters, which is 1.24 microns. It's about a micron. Right, so that's kind of on the upper, that's what we call the near infrared. Near infrared. So this would be 1,240 nanometers, right? That's another unit for visible length. So this is 1,240 nanometers. All right, and where is this unit useful? Well, it's useful in ionization potentials. Right? This is the units of electron. This is why we call it electron volt. Why it's useful. We use it for electronic information. So, for instance, and this is where we'll see it time and time again in this class after we get back from break. Right? What is the energy of taking hydrogen and separating it into a proton and electron? This number, delta E, is exactly 13.6 eV with plus or minus a few. We'll actually calculate this value precisely. It's exactly solvable value. All right, so we typically use EVs for things that have to do with ionization. It's the scale of ionization. Well, when we talk about electrons in bonds or in atoms, bound states of electrons around nuclei, EVs are a very natural number for us to use because the prototypical example of an electron bound to a proton has a bond strength of 13.6 EV. Okay, it's a really convenient number for us to use. So again, a bunch of different values. They all refer to the same thing. It's all about context for us. Okay, we want to use numbers that are easy to remember, easy to communicate, and are useful for the context in which we're doing our measurements. Right? It's not very useful for me to talk about EVs when I'm doing NMR. And it's not really useful to talk about megahertz when I'm doing an ionization. Right? And it's not useful to talk about joules in any of those situations usually, because they're typically very small as well. So we just take a unit, we stick with it, and then if we need to move around, we move around. I'm sorry, that was terribly boring conversation, but I think it's important. The reason why I bring it up, in particular with Homer 3, there's a lot of unit conversions. There's a lot of things with wave numbers, but you have to do a lot of calculations in SI units, which are joules. It's nice to have these conversions available. Okay. Let's move on. So last class we were looking at, oh, let me go ahead and pull up our lecture notes from last class. It might be this. No. Let's see. I wonder if these are notes from NMR. These are NMR notes. Okay, that's not what I want. That's the other class. Here we go. Right. So last class we were talking about the Morse oscillator, right? We realized very quickly that the harmonic oscillator is in some sense not a physical model bond, because it doesn't predict dissociation at all. It's a bond that is infinitely bound. It just gets longer and longer and vibrates faster and faster and faster, but in no sense do you ever break the bond. Right? So we had to get rid of that. We also, also described that at short distances, it's even more repulsive than a quadratic potential. It goes as hard as a 10th. Right? And then we know from experiment, turns out that near the bottom of the potential, it looks very harmonic, right? So we have something that's locally harmonic at low energy that progressively becomes anharmonic as energy goes up. Derive that potential here. And the take-home point from this was that we went from a situation in the harmonic limit where our energy levels, our ladders of the energy, the rungs of the energy ladder were equally spaced by h bar omega. So a reminder here, omega is in radians per second. H bar is in joule seconds. So this energy is joules. The way I define it. Right, equally spaced. And what happens when we go to the anharmonic limit is that we still have the roughly equally spaced character, but each level in some sense gets progressively closer and closer to the next one due to this anharmonic term that's defined by this value x of e, the anharmonic aromaticity constant. That goes as v plus 1/2 squared. Right? And what that leads to is when you do the algebra and you calculate the energy difference between two adjacent levels of the harmonic oscillator, that again, they're roughly equally spaced by h bar omega, but every v in some sense, each level gets closer and closer together, and that's largely generated by the magnitude of x of e. All right, and x of e tends to be somewhat on the order, I didn't write this here, but it tends to be on the order of about 10 to the minus 3, 1,000th of omega. Okay, so x of e is a small number. So when v is small, this is pretty small. Pretty small. Okay, and so the system largely looks harmonic when v is small. But as v grows, right, in some sense, the energy levels, progressive energy levels linearly get closer and closer together with a slope proportional to xv. Right, so what we would expect to see is that at low energy, we see a harmonic spacing, and then every time v goes up, they get closer and closer together. So let's look at some data and see if that's correct. All right, so let's test this hypothesis on one of my favorite molecules. One of the classic examples in physical chemistry is HCl. Now notice I write 1H35Cl because remember the vibrational frequencies of the molecule depend on the masses of the atoms. So the vibrational frequency of H35Cl is different than it is for H37Cl. Chlorine has two isotopes, stable isotopes 35 and 37. And so that would have a different frequency, right? So I need to be very precise about which HCl I'm talking about. And hydrogen, of course, has effectively three choices, but two stable ones, hydrogen and deuterium. And chlorine has two stable choices, 35 and 37. So I wrote 135 here just to be precise that we're talking about the most common form of HCl. Right, and what we can look at are let's just do some very basic spectroscopy. I'm going to make a little table here. And we'll look at the transition V plus 1, and we'll look at the frequency at which it appears, or the wave number in which it appears experimentally. And then we'll predict it with the harmonic oscillator. And we'll predict it with the Morse oscillator, right? Our anharmonic prediction or model. Okay, so we'll start with the simplest transition, the 0 to 1. This is at 2885.9. And let me go ahead and write down some numbers for you, actually. So let's just have them on the piece of paper here, some experimental numbers. So we could just, if you want to double check, you can. Promise you I'm not making things up. So for HCl, omega E, the harmonic constant. Oops, sorry. Wrong page. Come on, where are you? Sorry, I picked the wrong page. Sorry. Is 2990.946 minus 1. And omega E times XE, which is the anharmonic term, is 52.8186. Okay, so as you can see, X of E is quite a bit smaller, right? It's a pretty small number. And so we would expect that the harmonic oscillator approximation would give us a good prediction. And in fact, that's exactly what it does. Experimentally, we get it at 2885.9. All right, good agreement. And the Morse oscillator gives us the same value. So now we go to the 0 to 2 transition. This is what's called the first overtone. We'll talk quite about the spectroscopy yet. We'll get back to that when we get back to the class or from spring break. So 0 to 2 transition. This would be predicted to, this is experimentally seen at 5771.8 wave numbers. I don't trust the numbers I wrote down here, guys. I must be making things up. Okay, I see what I think I see what my issue is. So oh, I see what I'm doing wrong here. Sorry, let me erase this. I'm reading off the wrong column, guys. I apologize. The first row is fine. So the experiment for this is 5668.0. The HO prediction is off by quite a bit. It's off by almost 100 wave numbers. All right, so we can already start to see, and it's not too hard to calculate this, but this number is just twice this. Remember, they're equally spaced. So if the first one's a 2885, the next one should be a 2885 times 2, which is what we predict there. But in fact, the actual frequency is lower by, what is that, about 2% or something like that. It's about 2% error, give or take. Right. So what the harmonic oscillator predictions again is predicting equally spaced lines. But what we're seeing is that the lines are actually collapsing a little, but by a very small amount, right? We're only talking about a 2% variation here. And when we take the Morse oscillator results, we undo all those problems, right? And we get basically almost perfect agreement between the Morse oscillator and the experiment. Right? The idea is that this X of E, again, is a small number. It only generates 2% error in the first transition where it matters. but it's enough to really kind of drive your, I mean, 2% is not great here. I'll call that not a good error, in my opinion. Spectroscopically, we could do a lot better. Right, and just by including one extra term, right, all we've done is we've moved from a system that looks like, that has one parameter, omega E, we've gone to a system that has two parameters now, the small x of E. And we've already improved our system significantly. That's what I would call a nice fit, right? We're not really doing that much effort to improve our results. If we go to the next set of transitions, this is at 8347 wave numbers. And not surprisingly, the harmonic oscillator gets it, right? It's just progressively getting worse because the levels are not collapsing at all. And the real spectrum, the real anharmonic oscillator, the levels are not only getting smaller, but they're getting closer and closer. Sorry, the gaps are getting smaller between the levels. Not only are they getting smaller, but they get progressively smaller and smaller as you go higher and higher in energy. So not surprisingly, a harmonic oscillator works worse. And the Morse oscillator is still doing pretty good. Right, you can already start to see a little bit here, right? We had 0.2 wave numbers error from this, in the first overtone to 0 to 2. Now we have 0.5 wave number error. Right, so you can already start to see that there's a small disagreement starting to build, but again, it's very small. So when we go to the 0 to 4 transition, which I don't have data for, it has been measured. You start to see that error start to compound. And again, the trick to solving that problem is that, again, this 2-parameter approximation thing that we did here, 2 parameters, is just an approximation. As we start to climb up the period, up the potential, right, as we discussed, the system is getting more and more anharmonic as energy increases, right? We've gone from here to here to here, and energy. The potential is smoothly becoming more and more anharmonic as we go up in energy. And in some sense, that turns on the higher order terms. With the 2 parameters, we're assuming the potential is effectively cubic. But now that we get to the V equals 3 level, the anharmonicity's gotten big enough that maybe the 4th order term, the quartic term, is starting to turn on. You would imagine now that as we start to climb even higher, the 4th order term of the potential becomes more important. And then the 5th order term becomes more important. And that's going to require us to add more parameters to our energy. Right? We might have to include this quartic term, which has this y sub e term, instead of x sub e, it's the next anharmonic term for the next correction. Right? And I'm not really doing anything fancy here. Right? I'm just doing a polynomial fit of the data. This looks like a bunch of fancy stuff, but it's really, really simple. I'm just saying, hey, I've got some energies that should be equally spaced, but they're slowly moving away in a polynomial fashion from being equally spaced. That's something I can fit very easily in a polynomial, and that's exactly what I'm doing. Right? The polynomial quantum number v equals 1/2. So the systems are getting the energy level spacings in some sense are getting smaller as a function of v. And as the v gets bigger and bigger, the bigger, higher order term starts to become more important. Because x sub e is 1,000 times smaller than this coefficient, and this one's another 1,000 times smaller than this one. But in some sense, this one's going to grow fast. Even though it's small, it grows pretty fast because this grows as v to the 3rd, and this grows v to the 2nd. Right? So each of these little small terms, they get smaller and smaller and smaller, but in some sense, the importance of how they grow as a function of energy is faster and faster and faster because they grow as higher and higher orders of this polynomial. So not surprisingly, the more lines I start to append, I go to the 0 to 4, the 0 to 5, the 0 to 6, my Morse oscillator prediction is going to progressively get worse and worse until I add another term. Okay, so what we're effectively doing here, I use the word effectively because that's what we're doing. We don't really know experimentally what the potential looks like. but no idea. We're just making an approximation that looks something like a polynomial that becomes increasingly complex. More and more terms as energy increases. It starts to deviate from its quadratic potential. And so what we're doing is we're making kind of in some sense an effective model for the real behavior of the system. It's not a true representation of the model. It's just an approximation to it that's easy for us to fit and to have us kind of put us on a framework where we can compare different molecules in apples to apples. And we can fit any molecule we throw at it with this formula, get a value of omega E and X sub E and Y sub E for any molecule we choose. And I can compare all of them together. Some molecules will fit very, very well to the Morse oscillator, some not so much. Because again, it's an effective fit. It's an effective model. It's not a true model of the system. It's just this generic kind of simple model that we can apply everywhere that gives us good results. Okay? We make these kinds of choices in spectroscopy all the time. Is that there are issues, there are some things that we just don't know exactly, but we do know that up to a certain level of approximation, we can get really close to it, and we just use that approximation, right? Call it an effective model for the system. And people use effective models all the time. It's not unique to physical chemistry. Physicists use social scientists use effective models for things, right? Toy models and different types of things where we can compare diverse kinds of bodies of data, different types of molecules, all on the same kind of playing field. Okay, what time is it? Good. So what I want to look at right now, we're going to continue talking about spectroscopy when we get back. I want to just talk very briefly, kind of get us set up. We're going to introduce. Is there anything else from the problems that we should talk about? No, I don't think so. So what I want to do right now is to think about, let's go ahead and think about the spectroscopy a little bit. We don't really have time for this. You know what, guys? Why don't we just stop here for the day and enjoy the rest of our time? I think this is a good time to stop. We'll start with spectroscopy have a nice full day when we get back on Monday after spring break. Talk about the spectroscopy. We're doing pretty good on time. About a lecture and a half. I'm about a half a lecture behind, which is pretty good for me. We'll catch up eventually. So let's just enjoy let's just take another 15 minutes off, relax. You guys have a lovely break, so I don't see you again. Yeah, I'll take homework questions too if we want. So I got some time.
Thank you. I'll let you get yourself.
No, go ahead.
Yeah.
Maybe I'll do it on the floor. Right? Just sit down and just ask me. Or if you want me to look at something.
Well, you know why you put your music in too? I was like,
Good job. Like, we should. I want to You know, we lose the appreciation for those small things. It's like everything's got to.
Oh my God. Honestly, funny, Jack's the best person last one, never let it go.
Good. Rub it in her face.
That and criminal justice.
Yeah, see, have a good one.
I have some other great things,
Okay.
but it's that and criminal justice, so. You gotta give hours. Oh, the only other thing was I noticed, so for this table, like at the very beginning, that like it's supposed to be your values.
Yeah.
For when I'm filling this out, I obviously solved for alpha and I solved for K, but this I solved for the difference. I never actually solved for that value.
It should be the difference. Yeah.
Okay, and